This video is a supplementary video of the paper Dual Tendon Routing, a tendon routing for underactuated tendon-driven soft and wearable robots, submitted to RAL. Underactuated tendon routings have been used in soft and wearable robots due to its advantage of enabling adaptable motions with fewer actuators. However, previous underactuated tendon routings suffer from practical issues such as size, friction, and elongation issues. The most common method for designing underactuated tendon routing involves the use of moveover pulleys. However, this approach is generally avoided in soft and wearable robots due to the traveling length required for the moveover pulleys. This is because these robots are designed to be worn by humans, making the minimization of the end effector size a critical requirement. For this reason, researchers have developed their robots using only the fixed pulleys by removing the movable pulleys. However, this approach increases many curves in tendon routings, as shown in this figure. Since the friction occurs at the curve of the tendon routing, the friction applied to the tendon is not negligible in this routing. To solve issues from previous routings, researchers have developed a specific actuator that can contain the underactuation mechanism. Since the actuator has sufficient space, we can locate this mechanism without worrying the size issue. Also, the robot can be remained compact without suffering the friction. However, in this routing method, the tendon can be easily elongated because the actuator is usually located far from the end effector. Interesting thing we can observe from pros and cons of previous routings is that combination of UTRF and UTRS can leverage strengths of each routing while mitigating their respective limitations, providing solutions to practical issues. From this point of view, we propose a dual tendon routing that can resolve practical issues of the underactuated tendon routing. An interesting feature of this dual tendon routing system is its ability to generate 2 to the power of n plus 1 minus 1 unique tendon routings, where n represents the number of fingers. This is achieved by selecting different routing options at each bottom side of the tendon path. This diversity allows researchers to select the most suitable tendon routing to meet specific requirements. As a case study to show how diversity of DTR improves the robot performance, we applied this DTR design framework to exoglove that assists 2 fingers. In this application, we can explore 7 tendon routings as shown in this figure. The routing performance is evaluated by dividing the tendon into 4 sections, labeled 1 through 4, as shown in the left figure. For these sections, 5 performance indicators are proposed: adaptability, torsional balance, reliability, efficiency, and force transmission ratio. Detailed definition of these indicators are provided in our paper. After normalizing the indicators to a scale of 0 to 10, where 0 represents the minimum and 10 the maximum, the most appropriate tendon routing is selected based on the experimentally measured normalized performance metrics. However, directly measuring the tension in each section of a wearable robot is challenging. To address this, we designed an experimental setup capable of measuring the tension in each section, as illustrated on the right. After obtaining the tension distribution of 7 tendon routings, as shown in left figure, the most appropriate tendon routing for our application is chosen as TR3 by evaluating them with 5 normalized indicators. From the previous results, we have developed Exoglove 2, a next version of Exoglove, using tendon routing 3 that can reduce the hysteresis. Also, Since the friction at the flexor is significantly reduced, we could replace the extensor with passive extensor. Therefore, it was possible to use a single actuator. In addition, the robot contains a tension sensor at the glove in a compact size. This was possible due to the geometric benefit of this routing that the both end of the tendon is attached to the end effector. We have attached the rod cell at the end of the tendon in a compact size to measure the tension. The performance of the Exoglove 2 is validated using a dummy hand. Also, to show how the proposed routing has improved the robot performance, we conducted experiments with two robots, one with previous routing, TR2, and one with proposed routing, TR3. The first experiment measures fingertip force at two fingers. In this experiment, the robot with TR3 applied more even force to two fingers. Therefore, difference of fingertip force was less in the proposed robot compared to the robot with previous tendon routing. We also measured hysteresis of the robot. For this, angles of the index and middle finger joints are measured using motion capture cameras. When the robot with previous routing makes motions, the joints did not recover to its original posture, and the overall motion pattern was not uniform. However, when the robot with proposed routing, TR3, makes the flexion motions, the joint recovered more, and the overall motion pattern was more uniform. When we plot the same result in actuation stroke domain rather than in time domain, we can see more dramatic difference between proposed robot and previous robot. However, although the proposed routing successfully removed friction at the tendon, we could find a small amount of hysteresis. To further remove this hysteresis, we have used passive tendon as an extensor. The graph shows that the use of passive tendon successfully removed hysteresis. Dual tendon routing addresses practical challenges such as friction and tendon elongation by combining existing underactuated tendon routing methods. A notable feature of the TR is that it offers 2 to the power of n plus 1 minus 1 possible tendon routing configurations, where n represents the number of fingers. In this paper, we applied this DTR framework to develop the Exoglove 2. This approach provided several key benefits. It improved the robot's under-actuation performance by reducing friction, minimizing motion hysteresis, and enabled the use of passive tendons as extensor without the typical drawbacks. Additionally, it facilitated the integration of compact tension sensors. For further details, please refer to the project website and the full paper.